Alright, so last video we looked at transformations that affected the y values. Here we're going to look at transformations that affect the x values. Alright, now one way you can remember that, for instance, this transformation is going to affect the x values is, well, the transformation is happening inside the parentheses next to the x. Same here in this respect, that plus k is inside the parentheses, so we're affecting x values similarly here. Okay. As compared to the transformations which affected the y values, which we looked at last time. Those all happen outside of the notation f of x. Alright, so let's first look at f of negative x. And let's go to, I'm going to go to a screen. I'm just going to write down a function. Let's write down f of x, and let's graph x minus 1 cubed. So that's f of x. What would f of negative x be? Well, f of negative x would be, well, whatever I see in x, I'm going to put a negative x. And let's see what happens here. X minus 1 cubed. You get that picture, and if I graph f of negative x, what do I get? I get that picture. And this should confirm what we explored in class and what we noted here, which is that it causes a reflection over the y-axis. Right? And that's clearly what happened. Here's the y-axis, and it's acting like a mirror. Okay, and really what's happening, you can see, is that you're taking, you're multiplying all your inputs, your x values, by a negative 1. So if this is f of x, you can see that f of 3, for instance, is 8. Over here is f of negative x. And in order to get an output of 8, right, we can see here from the graph that to get an output of 8, we have to plug in negative 3. F of negative, that's that negative, but the x value we're putting in is negative 3. So it's f of negative negative 3, which is f of 3, which is 8. So in order to get out the same outputs as f, we have to plug in the opposite of what we used to have to plug in. Alright, so it's like taking your x values and multiplying by negative 1, graphically reflecting over the y-axis. Alright, let's clear these because we're going to need a different function next time for the next one. So that takes care of that. F of x plus k. Now this is something that confuses some students, so I'm going to look at it carefully, and the function I'm going to look at is, let's do f of x, and let's call that, just do our x squared, and let's do a shift. F of x minus 2 equals, well, wherever I see an x, I'm going to put an x minus 2, so it's x minus 2 squared. And then we might as well look at this as well. So let's see what effect that has. Now, actually, what I should say is that what everyone thinks is, everyone thinks, oh, you know, x minus 2, you subtract 2 from the x values, plus 2, you add 2 to the x values. That's not what's going to happen in this transformation. So take note of that. This does not add 2 to the x values. That does not subtract 2 from the x values in terms of the transformation. So watch why. We're going to see why in a second. But first, I need to convince you that that's not the case. So there's x squared, and here's x minus 2 squared. So what do you notice? You would think that, oh, x minus 2, that's a minus 2, it should shift the graph left. That's what everyone thinks. But remember, the blue is your f of x, that's your top one, and the red is your, and that's f of x, and the red is your f of x minus 2. And the result was not a shift to the left, right? This red one isn't the blue one shifted left, it's shifted right. it got shifted right 2. Right, so it took all these points and shifted them right 2. That's what the effect that had on the graph. Right, and similarly, if I do f of x plus 2, it's going to shift the graph to the left 2. So that x plus 2 shifted the graph left 2. So why is this happening? And I think the best way to explain it is to look at this, look at a numerical example. So if let's take, let's look at this case here. Let's say I do f of 4. What's f of 4? Well, it's 4 squared, which is 16, right? What do I have to plug in here to get an output of 16 over here? Well, in order to get an output of 16, I need what's inside the parentheses here to be a 4. In other words, I need what's inside the parentheses here to be a 4. But that means I need to plug in 6 for that. Right? I need to plug in 6 now to make that a 6 minus 2, which is f of 4, which we see is 16. In other words, I have to plug in a number that's 2 bigger than what I used to have to plug in. 6 is 2 bigger than what I used to have to plug in to get out 16. So you can see that, you can view that minus 2 as almost being like a handicapped. It's almost like a disadvantage on my inputs. It's pulling my inputs back, right? So to overcompensate for that, I have to plug in a number that's 2 bigger than what I used to have to do. So that's why this shifts the graph right too. So let's just make note of that so we don't forget. Shifts graph right too. Okay, and similarly here, if I want to get out an answer of 16, what do I need to plug in? Well, I have that x plus 2 now, so in order to get an answer out of 16, I need what's inside the parentheses to be a 4, which means I only need to plug in 2 here. So f of 2 plus 2, give me f of 4, which gives me my 16. In other words, I only have to plug in a number that's 2 to the left of what I used to have to plug in. Because that plus 2 is almost like, it's like steroids, it's giving the inputs a head start. Okay, so I only have to plug in a number that's 2 smaller than what I used to have to plug in. So that's why this shifts the graph left 2. Right, and that's what we saw previously. Okay. Counterintuitive, I know, but that's key to remember. This shifts the graph left 2, that shifts the graph right 2. So the last one is also somewhat counterintuitive. I have f of ax. So let's take a look at, we'll continue with f of x, but let's do, so I'll just write it down. F of x is x squared. Oops. F of 2x is going to be 2x squared, which you could also write as 4x squared, right? Because that's 2x times 2x, which is 2 times 2x times x, 4x squared. And then we'll take a look at f of 1/2 x, which is 1/2 x squared, which is 1/2 times 1/2, which is 1/4. X times x is x squared. Alright, now the common misconception again is to think that, oh, well, I'm just going to multiply my x values by 2. Alright, and I'm going to multiply my x values by 1/2. So that's not what happens in this transformation. Okay, yes, you're multiplying your inputs by 2, but what you need to understand is that the effect on the graph is not doubling your x values. It's cutting them in half. So let's take a look. Let me just clear this. And let's do f of 2x, which was 2x parentheses squared. Now again, Most people think that's going to double your x values, which would result in stretching the graph out, but that's not what happened, right? This is f of x, the blue. This is f of x, and this is f of 2x. So what do you notice? Well, what you should notice is that it compressed my graph horizontally, right? It's almost like you take your hands and push the graph inwards, right? It compressed it horizontally by a factor of 1/2. So in other words, f of x, when I input 2, I get out the answer 4. What do I have to input into this guy to get out an answer of 4? Well, I only need to plug in 1, which is half of what I used to have to plug in. And similarly, when I plug in 3 here, I got an answer of 9. What do I have to plug in to get an answer of 9 to this guy? Well, I only need to plug in 1.5, which is half of, and 3/2, which is half of 3. Okay, and similarly, if I graph 0.5x squared, right, that stretched my graph horizontally. So that's counterintuitive because there's a fraction in here, but what that did is it forced me to have to plug in bigger numbers in order to overcompensate for that 0.5 as an input. All right, so to be honest, I'm not quite so concerned with how you describe the transformation verbally, because I think there's so much room for error, but I do want you to understand what I'm going to leave you with this last little blurb, which I think will help you in terms of why this is happening. So f of x is x squared, right? I want you to imagine that you have a friend who owns a factory, and he has a machine that makes things. And so let's say he inputs pieces of wood and it makes wooden dolls. So before he'd plug in 4 pieces of wood, and he'd get out 4 squared. He'd get out 16 wooden dolls. Okay. But one of his friends works at MIT, and he came up with this really cool new technology that really helps production. It doubles all your pieces of wood that you input. So your friend from MIT comes along, and he introduces this new technology. Now, if I want to get out 16 pieces of dolls, rather, I only have to plug in a 2 now to make this 2 times 2. In other words, I only need to plug in half of what I used to have to plug in. Okay, so that's why you cut your x values in half by putting a 2x there. And similarly, if there was just some problem in the factory and all your inputs were slowing down your production, right? There was some, I don't know, it was an investment or something that was slowing down your production. Now if I want to get 16 out, what do I got to plug in? I used to have to plug in 4, now I got to plug in 8, so that this becomes f of 1/2 times 8, which is 4, which would give me 16. So I have to multiply twice. I have to multiply my x values by 2 when I have a 1/2 here. Okay? So, next video I'm going to do an applications video, which would show you the type of thing you'll be responsible for on a test or quiz. This video really should demonstrate, or I try to do as best I could demonstrate how transformations work. So I'll see you in the next video for applications.